Okay, welcome everyone again. So this talk was a challenge to create because it was one of those things where I knew what the message I wanted to say, but the delivery of it was difficult as to how to formulate it. So as you saw, I changed the title of it, instead of abusive propagation models and forward, kind of shortfalls and opportunities. I iterate on this. I think we're going to go with this for now. It is essentially broken into two parts. So we're going to talk first about the abuse of models, misapplication of models, shortfalls of how we do things today, and then a second half that's going to talk on essentially forward-looking, where really are some ripe areas for improvement. Some of these topics I have kind of some short examples, some toy problems, some are real life examples. I'm going to try, we got 45 minutes, right? I think that's what it is. Jeremy? I don't see any people. I'm going to assume we're 45 minutes. Okay, we got 45 minutes. I'm going to try to pause midway. So there's the outline. Like I said, kind of broken in half there. Assuming the time here, I'll pause and take questions after the first half. And then before going on to last and then taking questions at the end, just because perhaps people even want to defend some of these things to talk about at the beginning, and we can have a conversation on that before going forward. But we're going to roll with this. Now, I am going to say that I did pick, so for those of you who were yesterday, quite a few of you were, I picked on some models for certain things. I'm going to pick on some more I'm going to pick on some more models again today. Like I said, I'm pulling some things to real life examples of how things are used to kind of make a point. I'm not disparaging. There's perfectly good, valid reasons why things were done. We've all been involved in engineering compromises, or you just have time constraints. So I get it. I was in, when Claire talked about the ending up with a slant path model and a terrestrial model in 2108, I was in the basement of the tower at like 9 o'clock at night in a rainy March in Geneva until we finally got that out. And so I understand how the sausage is made there. But I think it's useful when we start to talk about things to kind of think about these problems and kind of lay them out, warts and all, and go from there. So with that, enough of the beginning part. Let's just jump in, kind of talk about some opportunities or some areas where I would say we fall short. So first, as I'm going to talk, is really incorrect model selection. So we've talked about this a little bit. We've touched on it just broadly here. But, generally speaking, there's two types of clutter models. And debate that if you want. Interestingly, I think, side note, the entrance of machine learning into this space perhaps is a kind of a third path or a different way to think about these things. But let's set that aside for right now. Generally, we have point-to-point models or site-specific models where we're saying we know all the information. We have a transmitter one area, antenna on it. They have a transmitter one area, and we have a receiver somewhere else. And we can sit here and we can pull data from LiDAR. We can pull building structures. We can pull, as they were talking in the fireside chat, we can pull all this information in, and we can try to say what's the most accurate prediction of clutter loss we can get at that area. And so great. We can make this computationally intensive. I don't care. These things perhaps aren't even moving. So if it takes a data compute, it's just a sunk cost and we move on. And that's great. On the flip side, we have point to area models or statistical models or site general models. These terms are all generally interchangeable. And here, instead of saying we have a point to point, what we're saying is, that's moth. We're generating a CDF, right? We're looking at, we don't actually know where these things are. We're modeling phones out in a city, across a whole city, a region of a city, along a coast, and these things are moving. And what we need is a CDF, and we want to do a Monte Carlo simulation. So we want to pluck values out of an ERN, right? Your standard statistical methods there. And so what we're really looking is a distribution of losses. And that's really what we're looking at. And these things deal with statistics. So we can't look at individual buildings on each of the locations. It's just not feasible, especially if you're doing analysis, United States is a big country. you're doing an analysis of the West Coast, even Google, I would venture would be difficult to kind of do a full large-scale Monte Carlo of an entire US deployment using LiDAR data. Like these things are very difficult to do. And so we use statistical models to do those. The problem arises when we select the wrong model for the problem that we're trying to solve, right? We have these different models, and we have general purpose models, that both clutter and general purpose models that fall into both of these categories. And sometimes, for convenience, for other reasons, we select modeling approaches that don't really align. So consider, we have some urban environment, let's say it's Denver, actually, and we're looking at deploying some base stations in Denver here. Generally, these are hung on the side of buildings. The little images didn't show up nicely when I put on the sides, shown on the top. But you have these panel antennas on the side of buildings, and that's how we're going to deploy. And off in the distance, we have some federal radar system, right? So your classic example, they're going to share a band. We need to figure out how do we do this, how much sharing is possible. And we're in Denver. We got some mountains or some terrain impact, right? So the question we want to ask is, how do we model the inference of the radar? Right. This is a very stereotypical problem, but if you've spent any time in this space, you've dealt with some variation of this, right? And so one thing you might just be like, okay, well, we have ITM, right? ITM does terrain diffraction. It handles a bunch of these things that we have to deal with. Perfect. Let's take ITM. Let's run it in point-to-point. We extract the terrain profile. We have some terminal parameters. Great. Okay. ITM spits out a BTL, basic transmission, right? Okay. So there's a start. These base stations are actually on the side of buildings, right? They're in the clutter. They're not really sticking up, as I can't remember which of the three talked about that. I think it was Stefan talked about that microcells. Apologies if it was one of the other ones are kind of going lower into the clutter. And so, okay, that base station is actually in the clutter. If we want to be accurate, we really need to consider some sort of clutter loss within this problem. So what do? Okay, well, Study Group 3 has a clutter model because ITM doesn't currently handle clutter or consider clutter, I should say. So let's take 2108, right? There's a clutter model in there. There's a terrestrial model. Okay, we'll take this and we'll add that clutter term onto the end. Now we have terrain loss. We have clutter. Problem solved. Right. 2108 is a statistical model. So what we've done is we've taken a point-to-point analysis using ITM, and then we've taken a statistical distribution. Now, many times I've seen people just pluck the median value from that distribution and say, there's your clutter loss. But that's really not what that model was designed for. That model, 2108 section 3.2, was designed to do Monte Carlo simulations of distributions of devices within enmeshed in clutter. One, that thing is fixed. That's a fixed infrastructure. There's no distribution of that base station. It's at a known location. Two, it's not really even enmeshed in the clutter, right? I mean, it's below the clutter height. That's true, but it's pretty much up there. It's not at street level, And so now what we're starting to do is we're trying to combine two different methods. And in one way, you're taking the shortcut by just taking the median and attaching it. And yes, you are considering clutter. It is better than not considering it at all, but it's not really a rigorous formulation of the problem. There are site-specific models out there that are more appropriate to do this than, say, pulling 2108 and attaching it to ITM. And one of the other things that leads into this is that we didn't even talk about variability. So people who were here yesterday, they saw this plot. I actually have this figure later in this slide as well for another comment. But right, Claire made mention of it, right? The details aren't important necessarily. The point is, this is 4 suburban environments that we took clutter measurements at 3.5 gigahertz. And the distribution of clutter loss ranges from about -3 up to 35 or 40 dB. That's a lot of variability just driving through what are nominally, in air quotes, suburban environments between in the Salt Lake region and in Denver here. Propagation modeling is non-deterministic. A lot of people don't like thinking in statistics, but we really need to think about losses. Even when we're thinking about point-to-point analysis like that base station, there's still some aspect of variability there. There might not be location variability. The terrain profile and the environment around it is not changing, but you still have time variability. Your atmospherics are changing throughout the year. We see this in data. So we need to think about, what do these variabilities really mean? When I say 80%, a location variability of 80%, do people have a conceptual idea of what that represents? Or when I say a time variability, or of what that represents? Or even more importantly, when we combine these things, right? Oftentimes you see what that bullet there. A system needs to be protected from interference 95% of the time from a distribution of UEs. How do we frame that problem? There's an easy way to do it. We can just take median values and say, there's your answer. That's perhaps an abuse of statistics, to put it one way. But we need to be more rigorous when we think about what these distributions are. And the last point I'm going to specifically call out is, sometimes we look at a problem and you see these statistical distributions and we say basically, there's margin in the system. We know all these distributions exist, but let's negotiate when we're doing, we're applying models as to what that protection criteria is, or what that variability, or where we are in that distribution. Let's negotiate that value and essentially abuse the statistics to achieve the goal, as opposed to actually, let's go back and look at what is the protection criteria, what is the interference threshold in the problem, right? We take the easy route and say, well, let's negotiate. I'll give you 80% because I think there's actually a couple of extra dBs in here. So we slide it down on a distribution. But I mean, really, we're conflating multiple things there. And it becomes hard to really look at that problem more rigorous when we start to kind of muck around in the distribution, right? I mean, these variabilities exist, right? So here on the left, if we look at time variability, right? On the left here, this is from a troposcatter link, but it demonstrates my point of time variability. Those axes are probably a little bit hard to see. On the top, it's 20 dB per tick mark. On the bottom, it's 10 dB. This is just over a course of 24 hours on 180 kilometer link. We're seeing swings in, and this has been removed. Fast fading has been removed. So we've processed out the fast fading of these signals. And what you're seeing is, you're still seeing 40 dB swings over the course of a day on this long distance link in just one day. And I believe this was in August. So that's just in the atmospherics before we even deal with clutter. And on the right, we had a question yesterday kind of about vegetation, and like, how does vegetation essentially change your clutter profile during the year? So on your right, we took measurements. The set of curves on the left were at an elevated terminal. The ones on the right were at essentially a horizontal terminal, and blue and red correspond to winter and summer, respectively. And what you see is that actually, this was just suburban neighborhood with a mix of deciduous and conifer trees. And you could even see swings of 3 dB just in a single neighborhood, just due to the change in vegetation. So you have a climactic distribution coupled with a kind of a distribution of the clutter that seasonally varies, combined with if you're having location variability. We need to be rigorous on what to do this. And yet we know this exists in the data. And yet if we go to model some stuff with TIREM only gives us, I mean, it doesn't have clutter in it at the moment, but it only gives us median loss. There is no concept of variability within TIREM. So when we're trying to solve a problem, we're not looking at the full range of what's going on. When we want to protect or understand what's the interference risk or some of the thresholds and these sort of problems that we need to solve, we don't have a model that essentially is acknowledging these statistics exist. And that's a problem, right? We need to be able to have the tools to kind of solve this. Going further in this route, this idea of so I touched on it in the first kind of example of tacking on clutter, right? There's reasonable evidence to think that clutter loss is independent from diffraction loss and troposcatter loss and some of these other propagation mechanisms. But it was not correct to say that clutter loss is independent from the model itself and from the path, if you follow what I'm saying there. So if you take something like ITM and then you just tack on P2108 to get the clutter distributions, on paper in checkboxes, you might say, okay, I've got train diffraction there, I've got some clutter loss. Let's say you're running ITM and in area mode, so you're actually dealing with statistics and it matches with the problem. Okay, I'm covering all my bases. That 2108 doesn't have any consideration of train geometry. It's just assuming everything's perfectly horizontal, and it takes that clutter distribution based on that. If you're running ITM in area mode and you're dealing with 2108, you realize you have two different concepts of location variability in your answer, right? You have location variability due to the changes in the train, right? Due to the statistics of the train as it undulates within a kind of pixel cell as you're doing your analysis. And then you have a location variability due to how the changes in signal due to changes in clutter within that pixel. Are we considering those? Are we combining those correctly? Or are we just kind of glossing over those as to what those represent? And of course, there's no consideration of mid-path clutter in particular. So consider this data that we took at ITS. And actually, this gets back to something Claire set up here. Kind of ideally, you should have one model. Okay, so we've taken a lot of measurement data recently at around 3 to 4 gigahertz, and what you're looking at there is, so basically, I took a subsection of that. It's at 3.5 nominally suburban environments, and I filtered out points that are geometrically line of sight to kind of get homogeneous. For those of you here yesterday, it's not perfectly homogeneous. We'll ignore that. For the sake of simplicity, I also removed kind of the box and whisker plots around each of those green points, just to kind of demonstrate here. But each of those points is a median value of a distribution. So what I did is you have the data binned up in 1 degree increments. So it's 0 on the y-axis, and then 1, 2, 3, and so in between there, each green dot represents the median clutter loss value within that elevation angle measured from the local horizontal, sorry, of those that set of points. And you can see the counts there. So first thing we notice is 21 actually matched really well to data. So that was very encouraging to see, right? At 0 to 1 degrees, our measurements in numerous different suburban environments matched surprisingly well with 2108. So that's great. Again, there's distributions there. 2108 has a distribution, and this data has a distribution, and we can dive into details of those. It's offline if people want to. But at the median of 2108 and the median of our data have really good agreement. So that's great. Second, let me acknowledge that those 2 points are likely should be omitted. I put them there for completeness because we had data up to there, but if you look at the counts of the data, they're not valid. But what's most important here is these middle parts, right? Even at elevation angles of 1 degree, you're starting to see noticeable decreases in clutter loss, right? So you go down from 30 to what, about 26 between 1 to 2 degrees, down to 22 at 2 to 3. These are terrestrial paths. These are very reasonable paths. If I'm sitting here in Denver and I'm looking west, even this far away from the mountains, you can have elevation angles at those sort of degrees, and you can see how far you start to deviate at the median already from 2108. To Claire's point earlier, I also agree that there really should just be a unified clutter model. There shouldn't be a terrestrial and slant path. That really, it should be unified because you don't need to be up at 30 degrees to see deviations. Even up at to 1 degree, you're already seeing decreases in clutter loss, and it just falls down. For obviously, this isn't a linear relationship because bad things would happen very quickly as you go into negative values. But we're seeing this right there. So when we take something like ITM or TIREM and we tack on 2108 or any other distribution of clutter loss, we're literally ignoring information. We have the train profile. We know what that elevation angle is within the general purpose model. We throw that away and we take this distribution and we pick that 0 value, say in 2108. That's the number we're using, even though we see this in the measurements kind of playing out, that even small elevation angles can result in decreases of loss. And so in this case, you end up actually over-predicting what sort of clutter losses you might expect at the median. Down tilt? We could talk details thing here. No, but so you're talking negative angles from the pointing receiver, right? Yeah. So the question is, what about negative angles? So this is angles measured from the local tangent to the surface of the Earth, so the smooth sphere. So you could technically, I guess, if you're going to the horizon, if you're beyond the horizon, have a negative angle coming up, but we didn't have data at that sort of thing. But the last thing I'll point to is this idea of using surface model data in a general purpose model. So the idea behind this is we take something like ITM or TIRUM or 2001, right? And it gives you a basic transmission loss based on a terrain profile and a bunch of other characteristics. And what we're going to do is, instead of passing a terrain data, we're going to push through a surface profile instead. We're going to build a surface model. We're going to pull the profile. And so essentially, instead of having terrain data, each point along that that array of data represents the height of the clutter, the trees, the buildings, all that information is contained there on that kind of vertical slice. And we're going to push that into the general purpose. So I'm familiar with things like TIRUM plus Clutter. And we're saying, well, the underlying physics of that general purpose model is then applied to this other sort of data, and we jump up with a prediction. Now, when we do this, that clutter loss that comes out, what you're saying is strictly a function of a vertical plane, infinite knife edge diffraction construction. That's what it is. It might be multiple edges, but you're saying that that's the only thing that clutter is dependent on. There is no reflections due to buildings behind a receiver. That's back reflections. There's no scattering off angles, because those models don't consider it from the terrain aspect. You don't have negative losses, because you won't get those out of ITM, TIRUM, or 2001. And for me, what's most important is that the result you get out of such a model can be highly dependent on the resolution of the surface model data you put in, such that increased fidelity of data does not always result in increased performance. So again, let's use an example here. This is a neighborhood in Boulder, and we took measurements. It's Drexel, for folks if you've seen measurements we've done before. This path that we're looking at is a couple kilometers, 2-3 kilometers long, maybe, around there. Importantly, there's a terrain ridge in between where the transmitter is and the receiver. And so you have terrain diffraction losses. You have clutter within, for those you saw before, the Martin Acres neighborhood, it's very similar. And so you have clutter and terrain. And okay, so the dotted line is the measurement data, what we get. And I know this is a little bit hard, but we'll distribute the slides and you guys can look in more detail. The set of colorful curves from left to right represent taking surface model data and putting it into TIRUM at increasing fidelity. So we start at 10 meters and 5 meters and 1 meter, and we go down to a 0.5 meter resolution that we process from LiDAR. And it's worth noting that the tail of that prediction matches really well. So when we're pushing in surface model data into TIRUM to predict what we're seeing in the Drexel neighborhood, the bottom, 20% of that distribution has a really good match. And not only does it match there kind of at that 0.5 meter resolution there, but we see the behavior which you'd want to expect, that as we increase the fidelity of the data that we're inputting in, we're getting increased performance out. Great, that's what we want to see. Let's take another measurement route we did. And so this is downtown Denver here. We drove these streets right outside the hotel, and we had a transmitter up. There's a church to the northwest of us that sits across the river. It's elevated, and we kind of put it up on a tower that they had. And so now we did the same sort of analysis. Again, the dotted line is the measurements. The colors are there. And one of the things you notice is that the same relationship we saw in the first one does not hold. We don't see great tail matching there. It's not clear that as we increase the fidelity of the resolution, that the results actually get better. In fact, depending on how you want to compare that, you could say at some point they cross over to be worse. And we see this through a variety of different data sets when we look at it, that there is no consensus as to how you do this, as to what you might see kind of in the results. And so you can't make any generalized, at least from my perspective, you can't make any generalized situation. Now you can tune, if you have measurement data, you can identify the resolution of data that optimizes your match for your modeling, but that requires you have data of your environments. Right now, I don't see any way to kind of generalize this. And so while on the left, it shows really well, that's not held across data sets that we had. I'll pause for 1 to 2 questions if there is, before I kind of go forward here.
So Bill, this is Masood. So one, you are talking about the shortfalls. I don't know whether you captured the fact that some of the clutter models that you are assuming it only takes into account clutter at the transmitter point or receiver point and does not take into account the clutter on the pad,
Right.
such as what ITM takes into account the terrain on the pad, but the clutter model that takes into account the clutter on the pad also might be a shortfall.
Yeah, right. So when we tack on a clutter part at the end, that mid-path clutter is just completely omitted. Now, and in some situations that might be valid. You may not have it; it's not a big deal. But yeah, there's no option, right? You're just looking at a distribution at an endpoint.
Hi, this is Rao from Charter. I'm a bit not sure I understood your definition of elevation angle, because I understood, from the model P2108 and so on, the elevation angle that they are talking about, I understood was that from the transmitter or the terminal to the clutter, top of the clutter.
Cool. Yeah, so I'm looking at elevation angle. So the question, I guess that you have a microphone. I'm measuring elevation angle as you would to your irregular terrain horizon. So it's referenced 0 degrees as essentially parallel, tangent to the surface of the Earth at where you're at, and you're measuring up to that terrain obstruction in the distance. So not to the top of the clutter, but to wherever your irregular terrain horizon lies.
And that's based on terrain horizon, based on terrain, not clutter.
Correct. So you're looking at the path from your receiver to where, in the absence of clutter, where is your horizon is there. Okay. Correct. So essentially then, if you're in so you're looking at downtown Denver, all points in a general area will have the same elevation angle. Whereas versus the top of the clutter, if you're doing site-specific, it would vary dramatically depending on where you are, right? So P2108 doesn't have any concept. Section 2.3 has no concept of elevation angle at all inside that. So I was pointing out that when you attach P2108 into a model, and if you have any sort of terrain interactions around you when you're you have this elevated horizon, but you can see how you can get noticeable decreases in clutter loss even with minor elevation angles, but there's not accounted for in the model. So you have the information in your analysis, but there's no way to actually use it and adjust what you'd expect your clutter loss to be for that. They have to be actually integrated, is what basically I'm making the argument that treating these two things as while the diffraction loss and the clutter loss might be independent of each other, that the actual base distribution loss, they need to be integrated together and take account for the full geometry. You can't treat the model, two different models, as independent of each other like that. Correct.
Hi, Ted Kaplan, RKF. Just wanted to clarify where something like 2108 may be applicable or useful. Like you said, if you're doing a very wide simulation over a very wide area like the United States, and noting that ITM is valid for paths greater than 1 kilometer where you're adding the clutter, you're talking about, for a lot of geometries, a lot of scenarios, very low elevation angles that far out for most of the statistics, although there are obviously exceptions. So if you're trying to build a model to show the probability of interference, the probability that something may be able to share rather than some deployment for a specific site, then it can be useful. You mentioned that the variability of a long path has a lot of variation to the multipath in the atmosphere. But that's usually not something you concern yourself with these types of interference because, first of all, unless you have a specific duct, you're not getting very large amounts of interference very far away. But for the desired links that can have very long paths, the availability of those links can be affected by atmospheric multipath, and so you use P530 or something like that to estimate the availability and the effects of the interference on that availability. So that's useful also. In terms of when you deploy, everything becomes a negotiation at that point. So you use the best models you have. You try to reduce risk as much as possible. I think that's where we're at.
Yeah, so I'm going to pause the questions right after this. And I'll just say, yeah, so there's a couple things in there. So yeah, so 2108 is useful where its assumptions hold, right? So like as I showed here, right? Like we see even in our measurement data here. So if you're in some coastal area and you're looking at distribution of UEs to some radar, perhaps off the coast where you're having your no terrain and your elevation angles are essentially horizontal, there's reasonable confidence that the distribution you're seeing out of that model is likely to be representative, right? As to what you're seeing. So you're there. But again, if you have other systems where you have terrain around you and you're in the country and there's mountainous areas, you do need to just be careful that 21.8 is assuming essentially a horizontal path and what that distribution is there. And so in those scenarios, just treating it in isolation, I would argue there's better ways, perhaps not formalized. Let me go on and we can come back. I still have some other people's hands up because I have a couple other examples I want to talk to. So the first thing kind of in where we really, things to kind of look at is, and Claire talked about this, and I'm going to pound the table when she said it, and I couldn't agree more. And those who were here yesterday heard me say this. I dislike urban, suburban, rural. It's very useful, all right? Clutter carriers are very useful historically. Pre-LiDAR and data, it was a very useful way to look at a map and draw boundaries around areas and think about what's going on. I get it. I would argue that the further subdividing of urban, suburban, and rural, the dense urban and dense suburban, and the various other things there is not a viable long-term solution. Within the US, it's going to become, right, you're really detailing into like what those terms mean language-wise, and then internationally, just the language translation and what those actually mean when you're trying to get very nuanced. You're trying to take something that's crude that maybe you can agree on and get extra nuanced it across regions. I just not viable. What we really need is models need to turn to objective metrics. They should be numerical, they should be calculable, and they should be computable based on an arbitrary area. So whether we're talking the entire city of Denver, we're talking about a neighborhood in Denver, whether it's just a couple streets, we should be able to arbitrarily set bounds of where we deem things. Obviously, we want to keep stuff homogeneous and compute, right? What really makes two cluttered environments similar? We had some discussion about this yesterday, and I got an example here to I pulled in some slides to talk to for those of you who are part of that, but we have these data sets. We have essentially ubiquitous 1 meter resolution data of the country. We have the software tools to process and use that and extract information. We should. Okay. This is the picture I said would come again. So the recap, for those of you who weren't here yesterday, we took measurements in 4 different neighborhoods between Salt Lake City and the Denver area, Salt Lake City area and Denver area. These are all nominally suburban environments. If you would look at them, they're single family homes with vegetation, trees in the area. And so it's the key says Martin Acres, Draper, which is south of Salt Lake City, Bountiful, which is a town kind of like Boulder, north of Salt Lake City, and Yale Crest, which is actually a suburban neighborhood on the outskirts of Salt Lake City itself. It's actually close to the University of Utah, just southwest of it. And so you could see, as I point out, you see these variations in clutter distributions for what those neighborhoods are, varying 10, 15 dBs, depending on where you're looking at those CDFs. So we have LiDAR data. So let's say we want to look at it and we want to look at what's the distribution of clutter heights So basically what we did is we took the LiDAR data, we processed it into a 1 meter resolution, 1 meter resolution rasters, and then we basically bin those raster pixels into 100 square meter pixel sizes. And we have a distribution of what is the average height of the clutter in those pixels that overlay with our drive route. And you see, and they're roughly the same. Draper's green, it's a little bit little bit different than the other two, but generally speaking, we see the average clutter heights are approximately the same. Again, these are all suburban. Kind of makes sense. You have vegetation and single family homes. That's there. But we can dig deeper into like statistics of describing this. I mean, we see there, we don't see a difference, even though we see differences in loss. But let's look a little bit deeper. There's some questions about, how else would you kind of think about clutter statistically? So this is a standard deviation of clutter heights within that, within those areas. And now we're starting to see some spread. So there's the same for neighborhoods, and we're starting to see some separation there. And by the way, I'm holding elevation angle constant to 2 to 5 degrees to try to create some normalization, so you're not kind of seeing a skew with the measurement data that's a function of elevation angle. So we're seeing clear deviations there, or clear separations based on standard deviation of clutter height. In addition, if we look at clutter density, so this is just the probability, or the percentage of an area that is covered by clutter, right? You have those 100 meter pixels composed of 1 meter pixel size, and what's the percentage of those pixels that are cluttered versus uncluttered. Again, we're seeing large differences between those environments. It's clear right in our environmental data. This is useful. This is, if we want to talk about what makes something suburban or what makes something similar to other thing, this is how we should start to be thinking about the problem. We should be analyzing the environmental data that's available and using this to localize our models and generalize them more broadly, as opposed to let's take urban and slide it, add some adjectives in front of it to make it more precise. As if we can do that with a subjective term to begin with. I would encourage us to think about things in this manner. And there's various other ways we can think about the statistics of the environment. I just pulled these out as some examples to kind of demonstrate here. I got 2 more slides, and then we can go back to questions here. I think it's 2 more. Machine learning and data science. I think we really need to embrace what is out there and what those tools can provide us. We're talking about increased measurements data. We're talking about better analysis of the environment. When I'm talking about statistics like this, we need tools to be able to sift through that data and help us identify the things that actually matter and what's important or what looks promising. You can't do these sorts of things in a manual way and think you're going to solve a larger problem, right? It becomes we have these data sources, and this is just one type of data, but it's not really practical to wrap your hands, right? Shiva mentioned we're going to be releasing around 6 million clutter measurement points at 3.5 gig or 3 to 4 gigahertz here shortly, and then you take the LiDAR. You're not going to be able to have that mental comprehension in your mind. There's a lot of information there, and we need the tools to kind of help us sift through it. But I would encourage us to treat machine learning and data science as a tool to solve the problem, and not as some sort of magic oracle. We just dump everything in and we get something out the side. If you look through the publications, there's different approaches to how machine learning is applied. Some people are doing those sorts of things where we're just going to put everything in, numbers come out, and problem solved. I would encourage us to think more carefully as what's coming out and merge. There are certain things that we do know about propagation in general. There are fundamental physics that we understand, or we at least have a grasp of. We can use that to augment the thing that machine learning does really well, and in a partnership between us and the tooling, improve modeling, right? So we should understand why the solutions coming out of it work, or attempt to understand what's going on, what they're gleaning insight into the data. What really is that insight telling us? And how can we incorporate that back into the physics and electromagnetics that we know? And part of that gets to the last bullet. And this is something that, if you think about for the past 100 years, we've had mathematical models to do propagation based on, electromagnetics and physics. And there's a lot of comfort in policy circles when they see those sorts of things. We do have to acknowledge that there's a non-technical issue that if I give somebody a black box that numbers come out and they don't understand what's going on, there's a we have to build trust. We have to build acceptance of those sorts of methods of what's happening. And that's not just a technical issue there. And so we have to think about, how do we better evaluate those sorts of methods? How do we incorporate what we know into those machines? There's a lot of promise here, but there's a lot of room, frankly, to be lazy. And so I would encourage us not to do that, right? We can use these tools to augment what we know and what we want to achieve in this space. I'll have 2 more slides. Sorry. Now I have 2 more. So this was kind of actually touched on the panel. I'm going to actually gloss over it pretty quickly here. I think there was a couple more questions people had. We need to avoid, Stefan, I think, said it. We need to avoid assumptions, right? So, you have these implicit assumptions in models sometimes, and we have to remember that the people who create the models are not, generally speaking, are not the same people who sit in the room and do the analysis. Claire mentioned, like, study group 3 sits there and builds these models, and then they hand them off to study group 5D, and they pick them up, and those people are going to look at them, and they're going to apply them to their problem. And there's not a lot of communication between that. There's not a lot of clarity of the nuances of where that model works well, how it was validated, where it's practical. And that's just how things work, right? Even within the US government, you could, if I generalize here for a minute, ITSO here in Boulder will work on the modeling, and then we hand it to OSM and they'll do the analysis. And so the folks at OSM, yeah, they're often technically interested as what we're doing, but they don't have the time to be involved in the whole generation of the model themselves. They're applying it to the problem. So we need to be better about how we make these things more clear. Antennas, I could talk antennas, we're going to skip that. But Stefan and a bunch of them said it, like, they're complicated, and blanket statement is simply assuming isotropic antennas really isn't valid for clutter models. When we're talking about scattering from different angles and rays and those sorts of things, and then we're looking at the real world where we have beamforming and dynamic antenna systems, the bridge between those two assumptions, the assumption and the operation is becoming really too great to jump across with just some hand waving after the fact. Let me go to my last slide. 4 minutes, right there. So technical transparency. I talked this before. We have a whole panel on this before. We need to get better engaging community. And really, when I say technical transparency, I think of 3 kind of core pillars. Publications is what traditionally we've done, right? We as a community, right? We publish papers. We say, here's results, here's findings. This is interesting. We move things along. I would argue that with every publication that we have, there should be a software implementation, either of that analysis or of that model, that's open source. And the data that was used to generate those results is also available, right? We need to be transparent enough that if we did something here at ITS, somebody can, any one of you could independently, if you wanted to make the time and the budget, reproduce that experiment and that result, whether it's a pure software analysis, to be a student doing in a lab in a course, they can reproduce it. If we can't do that, right, that limits our ability to collaborate and move forward. So we need to really move in that direction of all 3 of those on equal footing. It's not just publications are the gold standard and software and data are really nice to haves after the fact. They need to be treated equally and essentially bundled together with every step we take. And I'll stop there. I know we're getting close to lunch. People want to leave, but I'm here.
I'm out of time for 2 questions. Hey, Billy, by the way, thanks. This is incredibly cathartic. I agree completely with almost everything you said. But the one thing I would say is I would wish that you would add to your list. You talk a lot about the use of medians. If you can't use a random variable in your analysis, we immediately jump to the median. And that is just a terrible choice. I wish you would add that you should use the properly calculated mean relative to the scenario which you're trying to analyze. So if you ever get this brief again, that would be my one wish for this. The other thing is just on your Denver measurements, and I don't know whether you know this or not, but we ran into this very same problem 8-9 years ago, looking at ITS measurement data using Tyrum to make predictions of, and it's like, And it was like, use TIREM that doesn't do any multipath to predict propagation in a multipath environment. So turns out that when you actually switch to a multipath tool, you actually get a very good result as well. So it's just sort of foot stomping what you've already sort of said there.
Using the correct model for the problem is really key, and understanding what that model was designed for, right?
Yep.
Because if you could peer at a high level and be like, oh, the frequency range and the distance match up, and not realize that, yeah, but the problem space doesn't.
Right.
And so that's important.
Yeah. Anyway, and the last thing, which, and maybe it's really not maybe for you, but for a lot of these models, they're based on measurements, or they're validated or verified with measurements. But if you forget about the measurement bias, that's another abuse of the model, right? There's a measurement bias in there, and if you're not taking that into account, you potentially are abusing the model. Thank you. Great talk.
I 100% on that last point. And I know the measurement panel, because I was involved in prep, is going to talk about this, but the idea of diversity of measurements, that the UK measurement data set came up, and it's great because it's a bunch of different areas, a bunch of different frequencies, and it gives you kind of a completely different look there. And the measurement panel, I know, is going to talk about, perhaps we need to learn to work with less rigorous quality of measurements, kind of increased diversity. There's a spectrum there and a range where we can't have very expensive, high quality measurement systems out there doing measurements all the time. We need to think kind of more generally how we can extract information out of various different qualities of data.
Okay, last question.
Yeah, real quick. I'm still curious about the measurement as a function of uptilt. So you had it in 1 degree increments. What was the beam width of your antenna?
So these were omnidirectional antennas. Oh, there we go. Okay, so these were 2 omnidirectional antennas. And what I'm plotting there as elevation angle is from the receiver antenna, where is its irregular horizon distance? Or in this case, there is no, so in this data specifically, there was no irregular horizon distance because there's no terrain. So we're looking at essentially the line of sight angle to the receiver. But that would hold whether that was a terrain ridge that you were propagating over, that elevation angle would still hold there. So you're getting a diversity of elevation angles based on how you're placing the transmitters and where you're driving in distance.
Okay, so I understand that, but your beam width still comes into play here numerically.
Oh yeah, the beam width of the actual Omni was I believe 60 degrees. So we're not at the fallout region there. So it depends on what I'm plotting. So here I'm plotting clutter loss because none of these points had terrain interactions, and I removed the effects of free space because they're varying distances. All these transmitters were placed up on hills or lower in mountains, so you had free space down to endpoint clutter phenomenon. So you're looking at you have the basic transmission loss that you measured. We remove the free space component. All that's left is clutter because there's no absorption or things going on, kind of atmospherics when we did this data. So we're looking at data here. When I plotted here, this is basic transmission loss. So excuse me, when I showed these plots of the measurement data, or no, not there, sorry. Well, actually, this one's still valid. This one, actually, in particular, is of the Drexel neighborhood from Wing 4 of the radio building. Again, looking at the dotted line, that is BTL because that is both terrain diffraction and clutter loss combined, and free space, all essentially are the components of that measure. So yeah, depending on how I presented data, sometimes I presented it as clutter loss, sometimes I presented it as BTL. It's just a matter of what your frame of reference and how you want to do. And I believe I was consistent. I'm not, call me on it. I'm done. I'm around if you guys want to ask me any more questions. I don't know. Thank you, Billy.